talking about inverses of functions. We didn't call it that, but when you think of the word when you hear the word inverse, what do you think of? Opposites, right? So we found opposites of things. So what we did was we started with a set of ordered pairs. Everybody got a group and you got cardinal. What did you do to the x and y coordinates of your points? You switched them. So all the x and y coordinates switch. Okay? That is kind of the basis of being an inverse in algebra. Right? Algebraically, when you have an inverse, the x's and y's are going to switch. They're going to flip-flop. Right? So if you have a set of ordered pairs, we reverse the x and the y. If you have a function, remember the last problem on that paper yesterday? I came over and we switched the letters x and y and then solved an equation. So you have it. That's mainly what we're going to be doing in our class. We're going to be finding equations of inverses. It's kind of this B here. The main thing is you switch the x and y letters, reverse them, and then you have to solve for the variable y because you can't graph. Well, you can, but it's a little harder to graph something that's x equals. So we're going to make sure that we solve for y. That's mostly what we're going to be looking at today. Okay? Another thing we didn't talk about yesterday, but we made you write it, and nobody really asked me a question about it, is this weird function notation. When we graphed the first line, we wrote it, we said label that first line as f of x. And you all did that because you're used to seeing f of x. And then I said, we'll graph the second line f with this little negative 1 exponent as an x. That is the math notation for inverse. It's read, if you were going to like say it, f inverse of x, right? You don't necessarily have to write that down, but know that that's what that means. When I say f inverse of x, that's the notation I'm talking about. Right? Now, let's think about an implication or a result of switching our x's and y's. We're going to talk more about these two words next week, but think back to the function vocabulary we know. The set of x values or inputs. It starts with a D. What is that called? Set of x's. The domain. So we have the domain and then the set of y values is called the range. Well, if all my ordered pairs flip and the variables in my equations flip, then the domain and range are also going to flip. So the domain and range are going to flip as well. We're going to talk more about that next week. A little bit today, but more next week. And we're mostly working with lines right now, so we're not going to necessarily see it a lot, but in a month or so, we're going to be working with these really cool functions called logarithms, and we'll really see what happens when we do inverses there. All right? One more fun fact, because we're in the functions unit, and everything about functions is fun, right? Yes, sure. Oh, you're so not enthusiastic there. Yes, everything about functions is fun. Is that we graphed the line y equals x yesterday, right? We talked about that line. Do you remember what we noticed about the line y equals x yesterday on our activity? No? There was something. Something about the midpoints. Remember how you connected all those points, the ordered pairs, once you flipped them? And then we noticed all the midpoints of those lines were there? Well, the formal way to say that is that the original graph and its inverse reflect over the line y equals x. And some of you yesterday said, oh yeah, I remember the line y equals x from geometry. Well, in geometry, do you remember doing reflections and rotations? All right. We are going to do some reflections and rotations later on this year, but they'll be okay, I promise. Maybe, I don't know, we'll see. It'll be a little different in algebra, but here's what I want to point out for you here. When you were in geometry, let me extend this page here. When you did a reflection, you did reflections over a lot of lines, and you could reflect over the line y equals x. All right, and there was an identity, because remember you would do like quadrilaterals and triangles and reflect them over this line. And you had an identity, which is basically like a little formula for what you do with each ordered pair. So you start with the point x, y, and then does anyone remember what the identity for the reflected points would have been? rotation. There's no negative. It's just yx. Well, what happened with these ordered pairs? They flipped. Just like in our class, inverses, when they reflect over the line y equals x, their ordered pairs flip. So it kind of connects. It's kind of the same thing, used in a different way. Right? I know, I pained you to bring up geometry. I didn't mean to. But, I mean, I did mean to. I didn't mean to, like, bring back bad memories for you, though. Alright, that's like the most geometry we're going to do for a long time. Okay? Alright, so let's review what we did yesterday. Let's look at the first example here. We have a graph. We can all graph a line. So let's all graph the line 2/3 x minus 2. Now, I won't point out that this f of x is the same thing as y equals, just in case, but let's graph that line. And I'm going to move this line out of the way for now. Alright, so we start at -2. We have a positive slope up 2/3. Take a moment, graph that line for me. And I'm going to be a rebel, and I'm going to freehand the line up here. That was pretty good, though. That wasn't too bad. So we're going to graph the line. Now, yesterday, we started with a set of points. We plotted the points, we connected the points, and then in order to graph the inverse, that's what it was called, that second line, in order to graph the inverse, we had to take each one of these points and switch the x and y values. Which works, but who wants to switch all those ordered pairs? There's a faster way, and that's what you got to at the end of the activity yesterday, is dealing with this equation. How do I use the equation of the line to make it faster to find the equation of the inverse? Well, here's what you do. We said yesterday, we switch these letters, x and y. You just flat out rewrite it as x equals 2/3 y minus 2. Okay, you don't switch anything else, just the letters. And now it says solve for your new equation of y equals. So I know most of you know how to solve an equation, but some of us had trouble in both classes yesterday. So let's go through this one together. What would be your first step here? What do you move first? The 3 plus 2. All right. Now I know that seems silly to say, but some of us were a little off yesterday. And this is what I say to my Algebra 1 class. You put a bubble around the fraction. There's a fraction bubble. You have to make sure you deal with what's outside of the fraction bubble before you can get the denominator. So we have x plus 2 equals 2/3 y. Right, what would you do next? Now divide by 2. Multiply by 3. So you're going to multiply every single term by 3, which will give you 3x plus 6 equals 2y. And then you finish by dividing by 2. Good. Now I'm going to divide each term by 2 here because I know the 6 is going to simplify. So when you rewrite this, you'll get 3/2 x plus 3 equals y. Now we want to be formal here because it says right underneath, once you've solved for that new y, we're going to call that f inverse of x. Just to be formal, we're going to call it f inverse of x. Let's graph that line on the graph, and then let's talk about what we see. All right, so we're this time going to start at 3, go up 3/2. And you can connect that one. Okay. So you get 2 lines. The green one is my inverse. What kind of things do you notice about those 2 lines? Anything? You see anything that they have in common, different, or anything? They do intersect. Okay, they intersect. Are their slopes positive or negative? One of each. They're both positive. All right, let's look at the equations real quick. Let's talk about the equations, if it'll come up. There we go. Here's the equation of f of x. Here's the equation of the inverse. They both have positive slopes. What else do you notice about their slopes? This is 2/3, this is 3/2. They're what? They're flipped. What's the mathematical word that starts with an R? They're reciprocals. They're not opposite reciprocals, they're still positive, but they are reciprocals. So maybe make a note to yourself. The slopes of inverses are reciprocals. Right? That's one way to check your work. Right? When you're graphing a line or finding the inverse of a line, the slopes are always going to be the reciprocal of each other. Right? Now, I want you to graph the line y equals x. If you forget what the line y equals x is, it is the line with a slope of 1 that goes through the origin. Right? You graphed it a lot last year, but why don't you graph y equals x, and then we'll take a look. It goes through the origin, it has a slope of 1. Now when you look at that graph with y equals x on there, that third black line, what do you notice now? Anything? Can you see when I draw it on there how those are reflected over that line? Like they pivot across this point over the line there? Right? And then yesterday, we don't have to draw this on there, but this is where, if I connected these points, see how the midpoint of all those points lie on that line, just like yesterday? All right. Good. All right, questions so far? Flip your paper over. We're going to skip number 2. We're going to go down to number 3. That's not number 3. Here we go. Now, we are given a parabola here. This parabola is x squared. That's called the parent function. It's just the most basic parabola that we have. And this table represents all these points that are plotted on the graph. Now, we want to graph the inverse. So what do you think I need to do with these x and y values so that I can graph the inverse? What do I do with x's and y's for inverses? You switch them. So let's take all these x's. This top row here is going to become the y's, the f inverse of x on the bottom. So let's write those there. And then all the y values from the first table become the x's for the second table. And then I want you to take a minute, and I want you to plot those points. So 4, -2, 1, -1, and then connect them. My graph's a little pointy there. Yeah, have you ever seen a graph like that before? Like, so let's graph that one, and then it doesn't say this on your paper, but I'm going to also ask you to graph real quick the line y equals x. I want you to be able to see that on here real quick. So, I'm going to eyeball it this time. Can you see how the original parabola and the new graph have reflected over the line y equals x? Yeah? Okay, you can see how that happened. Now, what do you notice about the graph and its inverse? Do you notice anything about them? I mean, you probably notice things that you're kind of like, I don't really know what to say. So I'll kind of steer you in the right direction here. Let's look at the original graph, the one that's on the paper. First of all, is it a function? Yes, it's a function. Is it a 1-to-1 function? No. Okay, so let's make a note of that. So the original graph is not 1-to-1. It is a function, but it's not 1-to-1. Now look at the new graph, the one in purple. Is it a function? No. So the new graph, it's not a function, so it can't be 1-to-1. New graph is not 1-to-1. I'm sorry, I lied. I don't want to write that. The new graph is not a function. It's not 1-to-1 either, but it's not a function. Okay. So the original is a function, but not 1-to-1, and then the new graph is not a function. So you don't have to flip anywhere, but let me flip back for us here. Let's look at this first one we did. The green was our, or no, the pink was our original. Is the pink graph a function? Yes. Is it one-to-one? Yes. Okay. Is the green one a function? Yes. Is it one-to-one? Yes. So this one, I had two functions that were one-to-one. What happens is I'm going to skip down to the very bottom. There's a line. It turns out, it's already filled in here, a function must be one-to-one in order for its inverse to even be a function. Right? How do you tell if something's one-to-one? What test do you use? The horizontal line test. Right? So if it does that, if it fails the horizontal line test, you can still find the inverse, but the inverse will not be a function. So we're going to do one more thing. You're going to need your graphing calculator for this lesson. Let's try one more thing. Let's find the inverse of x squared algebraically. So we started with y equals x squared. That's your original. How do I find the equation of the inverse? What do I do with the letters? Flip them. All right. So I'm going to take x equals y squared. Now, what do I have to do to get y by itself here? Take the square root. All right, I'm going to square root both sides. And that's going to give me the square root of x equals y. That seems harmless, right? Seems like the right equation. I want you to graph. I want you to go into your graphing calculators, and I want you to graph the square root of x. I'm going to draw a picture here. So when you graph square root of x, I want you to see if you notice what happens on your picture. Doesn't look like what's on the board. Once you graph it, what do you get? It looks exactly like what's on the board. Do 6. Yeah, so like what do you get when you graph this? You only get half of it, right? You only get this top half. Now here's what I want you to do. I want you to keep that graph on there. I want you to go back to y equals. I want you to go down to the second line, and I want you to graph negative square root of x. Okay, so you should still be in there. You still have square root of x. But on the next line, I want you to graph negative. No, on the outside. All right, what happens if you graph negative square root of x? You get the bottom. So here's something you need to remember. This technically, when I take a square root of something, technically how many answers are there? Like the square root of 4 is technically positive 2 and negative 2. So this formula really should be plus or minus the square root of x. Now we will spend time later in the year working with graphs of square roots. But for now, one thing is that when our original graph wasn't one-to-one, we sometimes don't get the exact equation of the inverse in this situation. We're not going to like trick you a lot. I just wanted to show you that sometimes the equation does not always tell you the whole story about the graph. Okay? Good so far? All right. Let's pause for a second and let's see. So the top of this paper, we originally designed this was going to be different days, but we've been doing lines today, so we're going to actually skip 1 and 2, examples 1 and 2, and we're going to jump down to example 3. I want to do example 3 and example 4 because they're not linear. Most of the inverses that are easy to find are linear. Right? This one has a cubed in it, and the next one also has a root, an x to the 7th. So let's talk about how we would solve this. We need to find the inverse of 2x cubed minus 5. First step, as always, switch the x and y. We're at x equals 2y cubed minus 5. Now this one's not so hard, but what would you do first here to solve this? Add the 5. All right, so I add 5 to both sides. And it'll give me x plus 5 equals 2y cubed. Now, do I divide by 2 next, or do I do something with the cubed? I think you do divide by 2. Now, there's 2 ways you can write this. You can either divide both terms by 2, that's totally fine, or you can do divided by 2 all as one thing. doesn't really matter as long as if you can simplify, you simplify later on. All right, so I'm going to write it like that just because that's what I feel like doing. So now we have x plus 5 over 2 equals y cubed. How do I move a cubed root? You're going to take the cubed root of both sides. Now, does the cubed root go over the entire fraction, part of the fraction, all of it, none of it? The entire thing. So your inverse is going to be the cubed root of the fraction x plus 5 over 2 equals y. Now, we want to make sure that you're writing correct function inverse notation. So you need to make sure that you're right, that that's actually f inverse of x. Got to put that little f with the -1 there. Okay. That one is pretty straightforward. It's solved pretty much like the lines that we did on the last paper, except we had a cubed root. All right, good so far on that one. The last one we're going to do here is example 4. Now, example 4 is going to look a little bit different. I have f of x is 2 times the quantity x plus 4 to the 7th power. Right? We don't really deal with 7th power very often, but we're going to find its inverse. Let's switch the x and y. Let's start there. So x equals 2 times y plus 4 to the 7th. Where do I start on a problem like this? You don't know? Let me ask you, am I allowed to distribute the 2 here? No, I'm not. Here's why. If I did not have an exponent, if it was just 2 times y plus 4, then you would distribute. But because that exponent is there, you're not allowed to distribute. So since this is 2 times, I have to move the 2. How do I move it? Divide. We're going to divide everything by 2. We're going to make that 2 go away. Okay. At least that's gone. That makes it a little bit easier. So now I have x over 2 equals the quantity y plus 4 to the 7th. Well, now what do you think you do next? Deal with the 7 or the 4? The 7. So you're going to take the 7th root of both sides. So when you take the 7th root of the left, the whole fraction stays under there. And then the 7th root of the right-hand side makes the exponent of 7 disappear. We're not going to do a lot with 7th roots. This is probably the only one all year. So we have the 7th root of x over 2 equals y plus 4. Now it looks a little bit better. How do I get y by itself? Minus 4. Now if I minus 4, does the minus 4 go under the root, or does it stay outside of the root? Outside. So I have x minus, or 7th root of x over 2 minus 4 equals y, but what kind of notation do I have to write here instead? The f inverse function. All right, so that is the equation of the inverse. All right, so next week, not today, but next week, we are going to talk about how can you check your work, how can you know if something is actually an inverse or not, and we're going to do a proof. Now, I don't want to scare you. This is the most proof we will do most of the year. But we'll do a proof. You'll like it better than 2-column proofs. It's not 2 columns. We're not done though. Don't pack up, don't pack up. I lied. Or I didn't lie to you, but flip your page. There are 6 columns on the next page. I want you to do A, B, C, D, E, F, and then you can stop. We're going to do the bottom part next week. Try these 6. Here are the answers for the 6, so check as you go. I'm going to walk around and help you. If you